Today's vodcast is about ionic compound nomenclature and formula writing. Nomenclature is a fancy word meaning a system of naming things. So when you were born, your parents nomenclated you. You probably have a first name and a last name, and some of you have a middle name or maybe 2 or 3 middle names. Chemical compounds also have first names and last names, and sometimes they have a middle name. And what we're going to look at today is how to name compounds that we see that are ionic and how to write their formulas. We're going to look at the nomenclature or the naming of ionic compounds first. So listed here are the 5 steps for naming an ionic compound, and these are also found on the handout that you received in class, or if you misplaced it, it can be found on Pioneer Apps, or if you'd like, you can pause the vodcast right now and write these down. The first step is to confirm that the formula has a metal atom and 1 or more non-metal atoms. So you're looking to see if there's a cation and an anion present first. And as a reminder, metals are found to the left of the staircase on the periodic table, and nonmetals are found to the right side of the staircase on the periodic table. The main exception is noted here in that ammonium ion isn't a metal. It's actually made out of nonmetals, but it is a positively charged cation. So that's one to keep in mind. In an ionic formula, the cation is written first and the anion is written second. So you'll have a metal followed by a nonmetal. So something that's positive followed by something that's negative. And that will show up in a formula for an ionic compound only. When you name an ionic compound, the cations are named the same as their element. And if there's a transition element that can have more than one charge, you'll need to use Roman numerals to indicate which charge the cation takes. We'll go through some of those examples a little bit later in this vodcast. Step 4 says monatomic anions are named by changing the name of the element to have an IDE ending. So the name of an ionic compound will take the format of the metal and then the nonmetal with an "ide" ending at the end. Polyatomic ions will keep their own names. The ending does not change to IDE. Huge point to make you aware of is that prefixes are not used in the formulas at all. I have a box here kind of summarizing all of this. Ionic compounds have a first name, which is the cation, and a last name, the anion. So let's take a look at how to name some of these things, shall we? So let's take a look at the problems in the note packet that you have. Numbers 1 through 6, we have ionic compounds where the first element listed is a metal, and the second element listed is a nonmetal. To name the first compound here, which should be rather familiar, what we do is we name the metal, so that is sodium, and then the nonmetal drops the INE ending and turns to ide. So we have sodium chloride. Right. The second problem here has CSF. Now CS is also a metal, it's an alkali metal, and that is cesium. And it is bonded to fluorine, which turns to fluoride. Pause the vodcast at this point and try doing numbers 3 through 6, and then check them. Welcome back. Now check your answers for numbers 3 through 6. Magnesium bromide, silver chloride, sodium iodide, and calcium fluoride. Notice these are all ionic compounds that have a metal and a nonmetal bonded together. Numbers 7 through 12 are a little bit different. Number 7 I wanted to highlight because it has a sulfur attached, and sulfur has a different ending than what you might expect. A lot of times I see students write sulfuride, but actually that extra R drops off. So number 7 is actually written as aluminum sulfide. Alright, now numbers 8 through 12 have polyatomic ions. Polyatomic, poly means many, atomic atoms. So we have polyatomic ions. Again, we have a metal, or something that is positively charged as a cation in the front. Here's that exception with ammonium in number 9. And then something that is an anion, or negatively charged, at the back side, or at the second part of the compound. And in this case, these are polyatomic ions. Now, in numbers 1 through 6, we just had a single element. Here now we have atoms that are together. So what you want to do is refer to your ion chart to figure out what those things are. So for example, in number 8, we have Zn. Zn is zinc, so we named the metal zinc. And then you need to look up on the ion chart to figure out what NO3 is. And NO3 is nitrate. Okay. Number 9, we have something that's not a metal, but it is a positively charged ion. It's the cation known as ammonium, not to be confused with ammonia. And it is bonded to SO4, which, if you look on your ion chart, is sulfate. Take a moment, pause the video, vodcast, and try numbers 10 through 12. Now you can check your answers for numbers 10 through 12. Calcium phosphate, aluminum sulfate, and sodium hydroxide. Well, all of the compounds that we've named so far have had a first name and a last name, but sometimes ionic compounds have what we would consider a middle name, which would be a Roman numeral. When that happens is when we have a multivalent metal. So that's metals with more than one charge, which are usually found directly to the left of the staircase and in the D block, which I've highlighted here in this periodic table. There are 3 exceptions to this, and those are aluminum, zinc, and silver. Aluminum is always going to be a +3 charge, so you don't need a Roman numeral for that. Zinc is always a +2, and silver is always a +1 charge. And I remember that in that it makes a diagonal, kind of like a staircase, going down the periodic table, 3, 2, 1. And aluminum's atomic number is 13, and that's what reminds me of the +3, 3, 2, 1. Before we get into the nomenclature of compounds with multivalent metals, I think it would be a good idea to get out a periodic table and code it with the following numbers that will help us. These are called oxidation states or charges, just to help you get a sense for what we're going to be doing in just a moment. So if you get out a periodic table, the noble gases will have a charge of 0. The halogens have a charge of -1. And the chalcogens a -2. The nitrogen family a -3. The carbon family, it's a +4 or -4 depending on the situation. Boron family, it's actually aluminum on down, +3. And then beryllium, the alkaline earth metals, it's a +2. And the alkali metals along with hydrogen are a +1. This will help in our next piece. Alright, so number 13, we would start by naming the metal. It's lead, and then oxide. And I've left a space there because if you notice, lead is over here to the left of the staircase, which means it is going to have more than one charge. So we need to indicate what type of lead. Now I'm going to put a little parentheses in there to try to figure out, okay, what kind of lead is this? If we look at the formula for this lead oxide, we have PbO2. Now, oxygen, if you recall from just coding your periodic table, has a charge of -2. when it is bonded to something, all right? So if we look at our formula, it took 2 oxygens to neutralize the charge of a lead. So 2 times -2, all right, which would be -4, all right? There was only 1 lead in the compound to balance out the charge of those oxygens, so the charge on the lead must have been a +4. And to show that, what we do is we use Roman numerals in the formula to show the charge of the lead. So the Roman numeral indicates the charge of the multivalent metal, not how many there are, but the charge. Number 14 has copper, which is a transition metal as well, found over here, element number 29. So that is going to need a middle name. And then chlorine, which is over here with a -1 charge. So copper chloride. Now to figure out what kind of copper, we need to look at the formula. So we had CuCl2. Chlorine has a charge of -1. There were 2 of them. That's what the subscript indicates. So we multiply that by 2. -2. In the formula, there was only 1 copper listed, and that had to balance out the charge of this -2. So that means the copper must have been a charge of +2. And to indicate that, we use a Roman numeral 2 in the name of the formula. See if you can try 15 through 18 on your own. So pause the vodcast and try those on your own. And then check your work. Now you can see how you did. 15 nickel 2 bromide, and then we've got tin 2 iodide, cobalt 3 iodide, and tin 4 iodide. 19 is a little bit different than those that we just did. It's Cu2S. Each copper has a +1 charge to balance out the sulfur's -2 charge. So the name for number 19 would be copper 1 sulfide. Numbers 20 through 24 have polyatomic ions involved. So let's take a look at number 20. Number 20, you have lead, and then you need to look up the polyatomic ion, which in this case it is carbonate. Now, since lead is to the left of the staircase, we are going to have to figure out what kind of lead we have. So we split this up into its 2 parts, Pb, and then CO3. Now there's a little 2 on the outside of the formula for the carbonate, which means there were 2 of these. Okay, so when you look up the charge on carbonate, you find that it has a -2 charge. However, there were 2 of them in the formula, so that means there was an overall charge of -4. Looking at the formula, we see that there was only 1 lead. There's no subscript, so we have 1 lead in the formula, which means there was 1 lead needed to balance out the charge of this -4. So if this was a -4, the lead must have been a +4. So we show that in the formula by writing a Roman numeral 4. Try numbers 21 through 24. Pause the vodcast first, and then check your work. Well, let's see how you did. We've got lead 2 sulfate. Sorry. Iron 2 sulfate, not lead, iron 3 sulfate, nickel 3 nitrate, and cobalt 2 phosphate. Now we're going to move into actually writing ionic compound formulas, which you may find a little bit easier. You need to have a cation written first and an anion written second. So the positive thing is written first, followed by the anion. Use subscripts to indicate how many cations and how many anions are needed, so the overall compound becomes neutral. Subscripts of 1 are understood and they're not written. Be sure to use parentheses around polyatomic ions if you need more than 1 of them. And what I'm going to show you here is called the crisscross method. For example, if you have calcium and chlorine, so we have calcium ion and chloride ion here. Calcium has a +2 charge, and we can crisscross it down here. Chlorine has a -1 charge, that can go down here. When you crisscross, the number, not the charge, goes down, so 2 and 1. So the formula then becomes CaCl2. There's another example on your handout of magnesium ion, which is Mg2+, and phosphate, PO4 3-. Okay? Again, you crisscross the charges to go down like so. And in this case, we have Mg3, PO4 2. Now, if I leave it like that, it looks like I have 42 oxygens, which I don't. So you have to show that there's actually 2 phosphates, and to do that, you put the parentheses around. Sometimes you need to reduce the numbers. So let's say we had barium and oxide. If you crisscross that, you have Ba2O2, but that doesn't work. What you need to do is reduce that down to the least common multiple, which would be barium oxide BaO. There is a chart to have you practice writing ionic formulas in your handout. The chart looks like this, and what I would like you to do is to pause the vodcast and try writing out the formulas and then check your work. And here are the answers for the formulas on the grid. It might be a good idea to pause the vodcast here as well to check your work before you move on. And what I would suggest you do to move on would be to then name these compounds. There is another page to this packet which we will be doing in class. So that's the very last page of that handout, and hopefully you've been able to follow along up to this point, and if not, bring questions to class, please. Thanks.